Hello and welcome back to another module of EE5527 Sensor Arrays and Imaging. And this is where really we start our journey into the sensors or transducers or the antennas. So we are not yet talking about arrays of them, but we will start with a single transducer or a single antenna or a single source of some waveform which is to be generated. So we already know what is the role of a sensor or a transducer or a or let's not call it sensor because sensor is the one which senses, right? Let's call it source, transducer or antenna. So their objective is actually to create that disturbance, right? So we may create a disturbance using sound, we may create a disturbance using electromagnetic waves, but we need to create a disturbance. For that we need an antenna or a transducer. So we are going to talk in detail about what exactly is this transducer, and always think we always talk from the perspective of imaging. Okay, so if you talk about detection or if you talk about transmission of information, then maybe slightly different viewpoint you have to take. But of course some of the concepts are interchangeably used, so what you learn over here could be actually easily migrated and understood in another scenario. Okay, so let's move on. What is inside for start for us? Okay, so this is a typical imaging pipeline. Okay, so very generic. So I would like to highlight some points which is very important here. We need a source of disturbance, source of wave. As I discussed, this can be an X-ray source, it can be a gamma ray source, it can be an infrared source, it can be a microwave source, it can be a sound source. So some source should create that wave disturbance into the medium. So you do have the target scene or medium or space that you want to image. You need to create a disturbance in that using a source, and the disturbance will propagate through the medium, and whenever there is a characteristic impedance change, it will get reflected or scattered back to the source, right? So that's the idea. So we need to have a receiver to receive those echoes, okay, or receive the transmitted waveforms, whichever way you want to treat it. So we'll discuss that in more detail here. So we need a receiver to basically receive the data from the scene or from the medium. So we created the disturbance, but now we need to receive the disturbance after propagating through the medium. So that's the right way to put it across. And then once you receive that signal, you create the image out of it. So this is a pipeline. You take any damn imaging system, you take any waveform driven system, okay, imaging system, right from cameras to the modern day X-rays to microwave systems or even RF imaging systems. Any system that you take, the major workflow is something like this, okay. And now if you want to characterize this, I would like to broadly classify it into three categories: monostatic, bistatic and multistatic systems. So what are they? It's very easy, okay. So let's put some concept here. So I do have the medium, okay, so let's call it as the medium which I want to image. I don't know what is it, it is a black box for me. So I'll use some wave to disturb this medium and get the image out. It is known as monostatic if I have the source, okay, and the sensor, or let's call receiver. Actually let me just use the same terminology so that there's no confusion. So source of disturbance and the receiver, if they are one and only one, I mean one and only the same, then that is known as a monostatic system. That means it is like echo. You are disturbing the system by using the source, and you are having the receiver also at the same location. So it can be the same source itself, then it becomes a transducer. Don't forget that. If the source and the receiver are the same, it becomes a transducer, okay. So if we have such a system where the source and receiver are co-located, that is known as monostatic system. Please remember that, okay. Now this is monostatic, so let me name that here. So this is monostatic system. Then we do have the medium again. So let's give some example also so that it becomes clear. So this is ultrasound, okay, and then here also we do have a source, but the receiver is actually located somewhere else. need not be here, it can be here or here, but they are not co-located. But there is only one source and one receiver, but they are not co-located, so that means bistatic, as the name suggests. Okay, so bistatic. Here we will give some example. Okay, so let me just, I think some issue with the pen, so let me just come closer. So here some example is, if you take one example here, this is the X-ray system that we discussed, right? I think many times we took the example of X-ray. And then of course multistatic is, again you have the medium, and you have a source, but you can have the receivers at multiple locations. So basically one source is emitting the disturbance, and the disturbance is collected at different sensors. They are located spatially at different locations, and that is known as a multi-static system. So here example, I think there is a ring array systems, where you can actually mount a ring of arrays and then probably play with it. Okay, so I hope it understood. So if the source and the sensor are exactly located, or they are exactly the same, it is monostatic. If they are not co-located, they are separated, there is one source and one receiver to be exact, it is bistatic. And then if you have one source and then so many of distributed sensors or receivers, that is known as a multistatic system. I hope it's pretty clear, it's not that difficult to understand. Now some examples. You know that I already told ultrasound, right? This is a monostatic system. So you have a transducer which actually creates the disturbance into the medium. The medium, for example, here is abdomen, so you are doing an abdomen scan, and then of course the same sense the source which acted as disturbing the medium will act as the receiver here, so that's why it's a transducer. And then you have a very complicated backend, very complicated processing unit which takes these information from the receiver, multiple of them, and then of course reconstructs the beautiful image that we see. So this is an example. Another example, a bigger example, is aircraft tracking. All airports have this, right? You might have seen this. A bunch of antennas, RF antennas, which are mounted like this. They transmit the waveforms in the space, and then if there is aircraft anywhere near, it gets reflected, and then of course the same thing will receive, and then do have the processing here, and then maybe having a map, something like this. So these spots, the green spots that you see, are locations of the aircrafts. So this is not exactly an image that we see in the case of similar to an image that we see in the case of an ultrasound or an MR or a CT or X-ray machine or even the camera, but it is still an image. It gives you the location of the aircrafts from the station. So this is the station, the airport station maybe, okay. So it just scans and gives you the location. So this is kind of imaging that we can think of. So that's the beauty about, so different modalities, different imaging waveforms, basically electromagnetic or ultrasound or mechanical waves, it doesn't matter. The system, the workflow remains similar. Okay, so this is workflow. Now let's talk about the system. Because we are all engineers and we would like to treat everything in terms of system, right? And this, what you're seeing over here, is very, very, very interesting, because this remains similar in many different types of imaging modalities. So it doesn't matter whether it is actually ultrasound system or MR system or camera or radar system like we saw in the previous, but the chain, the signal processing chain, or the electrical engineering, electronics engineering chain remains same. So let's briefly go through what exactly is happening here. So this is actually, in fact, I have to tell you that this is actually the typical structure of a current imaging system, because old imaging systems probably will have mostly analog domination, analog circuits domination, but nowadays we do have most of the things doing in software and very minimal analog. So this is sort of the modern day imaging system. And let's go through this in detail, okay. So the fundamental thing is, like, we need to create a waveform, we need to create a disturbance in space. For that, what we have to do is we need to create a waveform, maybe using a DSP or using your GPU. You create a waveform, and then of course that waveform has to be converted to a voltage, right, an electric voltage, because we can only convert a voltage to a waveform. We can't really convert something digital to a waveform directly. So we need to convert using a digital to analog converter, which all of you are familiar. So you convert that waveform which was digitally made to an analog circuit voltage, and that voltage is applied onto the antenna. In the case of electromagnetic wave, you use the antenna to convert that electric voltage waveform into a wave, electromagnetic wave, and transmit into the environment. Similar to that, the same electric voltage can be applied to an ultrasound transducer and create mechanical waves and then transmit to the environment. So this is the transmit chain. Okay. So waveform generation, this will control, we will discuss that in more and more detail as we go in the subsequent slides, but this waveform generation will control the a lot of things actually. So there's a lot of flexibility that you have in modern day systems, because we do have that flexibility to generate that waveform, the shape of the waveform, the frequency of the waveform, all those things, amplitude of the waveform, everything digitally. They convert it to analog, and that is applied to the antenna or the transducer, which will convert it to electromagnetic or mechanical wave into the environment. And once it is there in the environment, it is getting received. Of course, we discussed that in the previous slide as well. It is received using an array of transducers or array of antennas, not just one, right? And then of course, that is actually again in analog in nature, because everything in natural world is actually analog. So you need to digitize it so that you can do all the beautiful processing algorithms, right? So you digitize that, so you need a digital, this is analog to digital converter, but it doesn't matter, the order doesn't matter, you understood I hope. So some part will be analog still. So we will discuss maybe at some point what is that is analog and what is that is in digital. Okay, but one important aspect is actually on the receive circuit. One important aspect that you should understand is there is a chance of doing some analog processing. We discussed about the time gain compensation, right, because the waveform will get attenuated as it travels. So towards depth it is heavily attenuated compared to a nearer depth. So what we need to do is we need to reverse that trend, right? So what we need to do is we need to amplify something which is coming from farther depth compared to something which is coming from a nearer depth. So those time gain control or analog gain control, we can actually do it in the analog part, and after that you digitize that, and then you do all the beautiful signal processing, which we will discuss in that forms actually the major part of this course. We create all the beautiful images. So that is very, very interesting, right? So this is the signal chain which is common to all the imaging systems, and very, very important aspect. So everything that we do is in time. So you generate the waveforms in time, you control the amplitude and the time period, in that way you control the frequency, in that way you control the wavelength, and that is getting propagated in space, and then the measurements, the receiver is also measuring everything in time. So that is a very important aspect. So we need to actually convert this time data to space data to have an image, because image, what we are trying to do is an image of a space. So we need to actually convert that time data which is measured in time to space, and that is what we call popularly as the beamforming algorithm, and we will discuss that in a lot of detail in the subsequent modules, so I will not spend much time here. So I will like to take the example of a camera so that you get a different feel. Okay, so in the case of a camera, you may not have any of this unless you are working on a modern day camera which has the depth imaging, or you are going to have something like light field imaging. Just search for that, light field. Okay, so there you may need to do some coded lights or some coded laser waveforms. So if you are not doing that, if you are using a conventional camera, you may not have this part because that's not needed. You may have a source which can be the natural source like sunlight, or it can be something like a flash, but there is nothing, no signal processing or no waveform generation or anything there. It's as plain as just a source of light. But then of course receiver part is exactly the same, but in the case of a camera we may not have measurements in time. Measurements in time in the sense like we may not have over a long time, but we only have a snapshot at a particular time instance, the measurement only at a particular time instance, and that is what we call as exposure, right? So when we close the shutter, what we have at the array of sensors is basically the value of light integrated over time, intensity of light which is falling on the sensors, which is integrated, which is accumulated, which is summed over time. So we may not have over every time, but we only have at a specific time. Till that time, what was the intensity which is falling on the sensor, which is accumulated. So that is a slightly different imaging system. But in general, what we do is we can only measure in time, we can only generate waveforms in time. Again and again I keep on repeating that, you may be bored with that, but I want it to get embedded in you. So we only have those measurements. So if you want to image it, you want to convert it back to the space. So we do have a time to space mapping, which is an integral part of imaging process, which we will discuss as part of the signal processing algorithms. Okay, so this is a takeaway. So the major takeaway is like you do have a transmit part, there is a lot of things happening there. You do have a receive part, there is a lot of things happening there. Now I want to spend a bit of time, extra time, to make you understand what is the processing components involved, because system on chip people are taking this course, so they should appreciate this. So waveform generation, as I said, is digital. So you typically have FPGAs or DSPs here, okay? And then of course the analog part, you already know the circuits. And then you have a variety of transducers or antenna to play with. And at the receive part, this part is mostly analog. And on the digital side, very high frequency processing. If your data is at an extremely high frequency, most of the time you do processing in FPGA, because you need a high frame rate or high sample rate operation. So you prefer an FPGA. And then you do sort of reduction in sampling rate, which we will touch upon, not in great details, but we will touch upon that process also at some point. Then if your sampling rate is reduced, then you may be able to do it in a DSP, or you may be able to do it in a CPU or maybe a GPU. So that is the components that you do or you choose in this imaging system pipeline. Okay, so this is it. So we will study all these beautiful algorithms in detail. We will not spend a lot of time in the hardware aspect, because hardware itself is a huge area to learn. So we will not go in there, but we will touch upon the beautiful algorithms involved in this space as well as in this space, the transmit space as well as in the receive space. Okay, so yes, I think maybe we will actually take this part also, and then we will stop. Okay, so transducers, source and sensor together is what known as transducers. So if you are working in microwave imaging or RF imaging, you call them as antennas. So you can take in whatever perspective, all these terms are interchangeably used in our course. So don't get very strict in their exact definitions, be liberal. So we just assume that it is source of waveform and sensor is nothing but receiver of the waveform. That is the meaning of it, okay, in our course. Okay, and with that understanding, I would like to, in fact, not I, but the major factors for the selection of transducer are shape of the transducer. Why? Because the shape determines the way the waveform is going to propagate, whether it's a plane wave transmission or whether it's a cylindrical wave transmission or whether it's a spherical transmission. It's all determined by the shape, and more importance to the shape, you will appreciate it by the end of this module. Okay, so there is something there in the shape of the transducer, so you have to be very careful. Okay, and then of course the size, that is also matters. So size does matter, right? It's very important to have an understanding of that factor. Actually, in fact, the size also determines the frequency. We'll come to that in a moment. Okay, so frequency is determined by the size of the transducer, and then of course frequency is what you play with. You of course have another factor, which is, I didn't mention it here, which is the amplitude part, but the amplitude is mostly controlled by your electronics, but the frequency is controlled by the transducer that you choose, the antenna that you choose. The moment you design the antenna or the transducer and you finalize that, there is no way you will change the frequency. It's not possible. So it's very important that you decide on the frequency, or in a way you decide on the wavelength priori, depending on the application, so that you are finalized on that. You can't change that much. Okay, so that's very important there. Now coming back to a very demonstrable example. So this is a typical ultrasonic transducer. So you can actually have similar pictures for a camera sensor or an antenna, an RF antenna or a microwave antenna. You will have a similar picture, but the concepts remain same, as I said. And going forward through assignments and all, I will encourage you to choose a different imaging modality than ultrasound and get used to what is going to happen. Similar picture you can actually draw there. Okay, so this is not a very complex picture. Don't get lost in all the markings here. I will explain it to you very simple. You obviously have a case. all the time. Whatever transducer and antenna that you choose, you will have a casing. And then the most important aspect is right down here. So you have an electrode, 2 electrodes, and a piezoelectric material. This is an ultrasound sensor or ultrasound transducer rather. So you do have a piezoelectric material and surrounded by 2 electrodes, and one electrode is going to the signal and the other one is going to the ground. So a high voltage will be applied across this, and that voltage is decided by who? We will be deciding, the waveform will be deciding that voltage and the shape of it, or the pattern of it, how you want to excite these electrodes. So that is coming from here, right? That is your digital system sitting somewhere here, and that is giving this signal here, and that signal is applied across the piezoelectric material between the electrodes. So that material is placed between the electrodes, and of course you want your wave to propagate in the forward direction. You don't want to go in the backward direction, right? You want to suppress anything which is, you want to damp anything which is going backward, because I want to image in front. If everything is coming from all directions, I will be confused. Imagine the reflections are coming from all directions, you will be in a lot of trouble. So for that you need to put a backing material which is shown in the red color here. So that is like a dampener, it will damp anything which is going in this direction. So you don't really want the waveform to go in this direction. So if something is going, this guy will say that no, I will damp it, you only should go in this direction. So that is the meaning of it. So there's a backing layer, okay? So that is here, so it's like a dampener. And then of course you do have something which is very important, which is the matching layer. So we know that whenever we place the transducer on a body which we want to scan, let's it be a human body or some non-destructive application where you want to scan a metal, so we will place the transducer on that foreign body, but there is a huge impedance mismatch between the transducer and the body. So to prevent that, what you do generally is a matching layer, so that you avoid that start reflection to an extent possible, to the extent possible, okay? So it's all on the characteristic impedance, you try to match it so that the reflections that is coming from these interface mismatches are avoided or minimized to the maximum possible extent. So if you have gone for ultrasound scan, for example, you actually put a gel on top of the probe. So that is actually to reduce the air in between, because when you put the probe on the body, there is a chance that the air will come and sit in between and it forms a layer. And you know that air, we already saw that air will act as a huge specular reflector, and there will be a lot of reflection coming back, and that will screw your imaging, right? So to avoid that, you put a gel, so it will be acting as a matching layer, an additional matching layer to minimize that air bubbles in between. Okay, so that is it. So the major part, if you want to put this way, there will be a source generator, so that will be like an electrode, and then followed by a piezoelectric in this case. For an antenna case, an RF antenna case, it will be something else, but there will be a source generator, that is the disturbance generator. There will be a backing material which will not allow the wave to propagate in the opposite direction of imaging. That direction will be completely damped, so that is the role of the backing material. And then of course any time there will be an interface created between the antenna and the environment. To want to minimize that, so you go for the matching layer, okay? So I hope this part is very clear. Now coming back to the frequency aspect. So this is very important. The resonant frequency, or the frequency that is going to get generated, the frequency of the wave that is going to get generated by the transducer, is determined by the thickness of the transducer. In this case, the thickness between the electrodes, you can say. And it is given by C by 2D. I will come to the derivation. It's not a very super difficult derivation. I will explain to you. I will try to explain to you rather. D is the thickness of the material. C is the speed. Okay, very, very important. So it is actually, the material has a role. So in fact, I will share a document with you, so you will see that. Okay, material. The moment you choose a material, you fix the speed. So material has definitely a role in choose, but the moment you decide to fabricate and you decide on the material, then that role is done. So this is particularly applicable in the case of ultrasound. It may not be that heavy dependence on the case of electromagnetic wave, because electromagnetic wave doesn't depend on the medium for propagation. But ultrasound, it is very important that you choose a material which is good, which gives you high, depending on the frequency that you want, you choose the speed, you choose the material, then you choose the speed. But this is also, once you choose the material, that's it, done. But the thickness has a role. So as you can see over here, a lower thickness will increase the frequency, higher thickness will reduce the frequency. And if you put the values here, C by F0 is lambda 0. So if we rearrange this equation, you get something like d is equal to lambda 0 by 2. But in fact, the derivation is actually the other way. You derive this first and then you go to this. I will show you why. Okay. So this is a very interesting example that I am going to put. So let's put the two electrodes here. So these are the two electrodes, and you have a material which is actually lying here, and this is actually the distance d. Okay. So that is the distance d. Now these two materials are fixed, right? These two materials are fixed. They are not allowed to vibrate because those are the electrodes and they are actually fixed, like rigid bodies. So, but we know that for the resonance to be created, ideally what we want is to create a standing wave inside, right? Go back to the lecture. So standing wave is what actually appears like resonance, right? So what we want actually to create ideally is a standing wave here. So how to go about it? So what is the lowest frequency standing wave that I can create if I have the distance like this? So it will be something, let me use a different color so that the explanation becomes more colorful. Okay, so let's use green. So the smallest waveform I can create is something like this. So this is a node, this is another node. In wave terminology, node means fixed location. It will not have any motion, it will be fixed. So these two guys cannot move. So the smallest wavelength that I can create is this, right? 1/2 cycle sort of. So this will go up and down, up and down. And what is actually this wavelength? Let's say lambda 0 is the wavelength of this particular waveform. So what is this distance? D is equal to. So D is equal to 1/2 cycle. So half cycle means lambda 0 by 2. So this is basically this guy over here. So now lambda 0, we know that lambda 0 is nothing but C by F0. If you put it, you get this expression. So actually this should be reverse. Okay, but since I told you that frequency is a factor of selection, that is why I put this way, but this is the derivation. And this is actually, this lambda 0 has a beautiful name. It is a fundamental wavelength. Okay, and the next one I can actually create from this is something like this, right? Because this has to be 0, because they are not, the velocity here has to be 0, so it has to be 0 here. So this is the second one I can choose, and this is actually the second harmonic. Okay, so this is basically the second harmonic. This is the fundamental. I think there's something serious with my pen, sorry for that. And this, some people call it as first. Maybe I have to reduce the speed of writing. Okay, so first harmonic also some people call that. So from the fundamental only we are deriving this beautiful expression. Okay, and from this expression it clearly tells you that if you want a high frequency, you want to reduce the thickness. If you want to have a lower frequency, you want to increase the thickness. So keep that in mind all the time. So the thickness of the material determines the frequency of the transducer. Very important point. Okay, and now just another viewpoint here. So again you have the active element here. This is the active element here which is shown, and then you have the backing. Of course you have the electrode between these two material, and then you have the matching layer, and you can see the wavelength is lambda by 2. And interestingly, the matching layer, I'm not going to the details of that because it's not very important for us, but it is interesting to see that the thickness of the matching layer will be made such a way that it will be lambda by 4, and that is like the quarter cycle. That means the node will be having opposite vibrations. One will be positive, one will be negative, and that probably is to cancel out any echoes which are coming back. You want as much to be propagated forward, you want the echoes to be coming back. So those who are specialized in antenna design could actually throw more thoughts in that direction, the matching layer thickness. But yeah, let's not spend a lot of time into that details, but more important is this guy, the frequency. The choice, it depends on the thickness and of course the material that you choose in the case of an ultrasound transducer. Okay, so in the case of an electromagnetic antenna, the C may not play much of a role because it is fixed, but D will play a lot of role. Okay, the thickness of the material. Okay, so with that I think, yeah, with that I will stop this session. Okay, so maybe this slide also, sorry for that. So because this is quite easy to explain. So the expected frequency, so all thing that I talked about in the last slide, the expectation was like I will create a single tone, a one frequency waveform. But that is not going to happen because we know that the transducer material, ideally speaking, is composed of smaller particles, so they are going to vibrate and they will not create exactly the same frequency. There will be some material mismatch. So instead of a single frequency, you will get a bunch of frequencies, and this is also added by the dampness, right? The damping that you do on the backing layer, that also creates to that. So for example, I think I'll explain with this particular chart. So the expectation was like you have a single tone at f0. Okay, if I plot the spectrum, if I have the x-axis as the frequency and y-axis as the amplitude or the magnitude, the expectation was like I have a single tone here, a single frequency here, a single peak here. But because of what I explained just now, you won't get that. Instead, you get a band around this single frequency. Okay, and this is what very important, and we call this distance, the difference in frequency when the amplitude drops to half, we call it as full width half maximum, or in signal processing terms we can call it as bandwidth. Okay, so bandwidth of the waveform. The ratio, the basically another important factor which if you coming from electrical background you might have heard this term, is the quality factor or Q factor, which is the ratio of f0 by bandwidth. Okay, so a high quality factor either could mean that your sender frequency is high, but let's say the sender frequency is fixed. So if the sender frequency is fixed, then if a high quality factor essentially means that your bandwidth is small, right? This value you want to increase or you want to reduce the denominators, your bandwidth is small. That means essentially you want to compress this guy, this width you want to reduce it to smaller width, and that means the signal will become more and more like single tone, right? You have a single peak here, that is like the ideal scenario. That means the bandwidth is sort of zero, the quality factor is sort of infinity in that case. Okay, so the ideal scenario is the quality factor high means typically you will have a single tone signal. Quality factor low means typically you have a wider bandwidth. So there is an intricacy there, I will explain with this example. So of course the design of transducer, everything is determined by the backing layer and the matching layer and all those things together. It's not just about the transducer, only the electrode and the material in between is not alone determining that, but the entire transducer setup is going to determine the Q factor or the shape of this particular wave in the frequency domain. Okay, and then high quality, as I said, means narrow bandwidth or single tone, and they are ideal for oscillators. For example, all continuous wave application, you want a continuous wave, single tone wave to go through, then that is ideal scenario. Oscillators, how if you go back and see the oscillator literature, you will see that there is a crystal placed in vacuum. Right, the vacuum is something like preventing, there is no damping there, you are allowed the waveform to be exactly single tone. So there is no damping happening, you are not going to damp the waveform. Or now so the computer science people, electrical people might be thinking that damping creates widening or damping creates bandwidth, damping removes it from single tone. Yes, we will see that in the next slide. So oscillators are designed such a way that the crystal is vibrating, but then you have vacuum around it, so there is no damping happening. That means you will be able to achieve extremely low bandwidth or extremely high single tone signal, and that is what you need in the case of an oscillator, right? You need a clock which is extremely precise, right? So that is what you do it in an oscillator. Or if you want a continuous wave application, which we will not talk in this course, but there are Doppler applications, Doppler shift and all, where you need a continuous wave which is going and coming. So that for those sort of applications you desire a high Q. But in the case of a ultrasound or an imaging or any sort of imaging application, your objective is actually to have a low Q. The reason I will explain with an example in the next slide, because we need some pulse to go. We don't need a continuous wave to go, right? For a continuous wave to go and come back, it's really not imaging. In imaging, what we need is we want to send a narrow pulse. We want to restrict the thing in time. You want to damp the waveform so that it won't extend infinitely long. You want to restrict into a narrow pulse, and moment you restrict in time, you are going to expand in frequency. Okay. So those who are not understood the Fourier transform will have trouble in understanding that. So based on your knowledge of Fourier transform, even I can schedule a separate video lecture on Fourier transform if a need arise. But you just consider this, frequency and time are dual. That means anything which is expanding in time will be compressing in frequency, and anything which is expanding in frequency will be compressing in time. It's a reverse of this. Okay, so we'll explain that using this particular chart. So assume that you have a infinitely long, so we can't really create a signal which is infinitely long, but I am just taking in MATLAB or Python something which is occupying the full time. So I have a time and the signal is occupying the full time. Okay, so that's a meaning. And if I take the Fourier transform, so the x-axis is frequency and y-axis is amplitude. So what you see is a single tone signal. Okay, so there is one tone which is at 10, this is a 10 hertz waveform. So this is at 10 hertz, you see a single peak. But now suppose let me dampen this. Okay, so I am going to damp this signal. I won't extend it all 100 samples or 100 seconds in time. I am going to dampen it. This is exactly happening when you have a matching layer and a backing layer in your transducer. This waveform will not be extending, it will get damped. So basically this is in time, so you will get damped symmetrically. And what is going to happen is, you see, notice compared to this, the Fourier transform is expanding. So you restrict in time, you are going to expand in frequency. That is going to happen. That is why you do have a bandwidth now compared to this. And if I further damp, so I again damp the signal to something like this. So very limited, it's like a pulse now. So I damped it to this extent, then you see the width, the bandwidth is increased compared to this and this. So this is like a single tone. And now I have a bandwidth, and there is instead of a single frequency, it will have multiple frequency. That is the meaning of it. So this waveform is, ideally speaking, it cannot be expressed as a single tone. It can only be expressed as a sum of some single tone frequencies, and that forms the bandwidth. So let me put the thing here. So this is the bandwidth that we were talking about, and then this is the sender frequency. So this is your F0 and this is your bandwidth. Okay, so that's it. So yes, so that's it. We will stop here, and then we will think the sensor design, the transducer design, the antenna design from the imaging perspective in the subsequent slides. And there are factors which are important, which are driving the transducer choice. So whatever we discussed so far is like the transducer, the design is, we talked about the imaging system in general, then we discussed about the imaging pipeline, the signal processing pipeline, and now we are slowly starting off with the transducer. And the shape of the transducer is important, the size of the transducer is important. You realize that in the last slide, because the size actually determines the frequency. The frequency actually determines the wavelength. And the wavelength actually has an importance, or the frequency has an importance, which we will discuss when we talk about the resolution and all those aspects. But it's important to see that the waveform is not infinitely long. We will damp it, and the moment you damp it, you will not have a single tone. Instead, you will have a bandwidth around a sender frequency. So that is very important. So the takeaway from this slide is actually the transducer, even though we call a sender frequency for the transducer, a resonant frequency for the transducer, a resonant frequency for the antenna, but that is not strictly one frequency. There will be a band around it. The reason for that is we are going to damp it. Okay, the signal will be damped in time, and that is ideal for imaging, because I don't want to send a waveform something like this. If I send a waveform something like this, that means the wave is always on, and there is nothing like a reflection mode where I am listening to the signal, right? So imaging is all about listening to the signal. So if you want to listen to the signal, I want to reduce the extent of time. I want to have a finite pulse, something like this. But the moment you do this, the bandwidth is going to come up. Okay, so it won't be no more a single tone like this. It will be expanded in frequency. You will have a sender frequency and you have a bandwidth. So certain technical terms that we introduce the frequency, we introduce the wavelength. These were known to you already, but we introduce another thing which is known as the bandwidth. And of course, the ratio of the sender frequency to the bandwidth is known as the quality factor of your transducer. Okay, so for applications like Doppler or oscillator, you want a high quality factor. For imaging applications, you want a low quality factor. Okay, so with that, we will stop this particular lecture. There will be some more lectures which are coming up, which will discuss about the resolution aspects. So till that time, it's bye from my side. Thank you.